Okay, I think everything is ready. Maybe we can start the guest lecture today. Okay.
Okay.
Ya, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Dear Associate Professor Hirofumi Dohi, once again, thank you for your attending here in our guest lecture. So before we start the lecture, first of all, I would like to probably introduce you to our student here. Dear students, our guest lecture today is Associate Professor Dr. Hirofumi Dohi. He is now an associate professor at Chiba University. His expertise is really specifically regarding about the synthesis of carbohydrate derivatives, which can be used in healthy functionality. So if we have looked to the his research interests, he is focusing on efficient functionalization of glucose development of companion synthetic procedure for an acetyl monosamines, and also elucidation of structural dependence in the surfactant activity of monocyl erythrotyl lipid and development of highly functional surfactants and anti-biological agents. And last is elucidation of structure dependence in the surfactant activity of monocyl erythrotyl lipid and development of highly functional surfactant and anti-biological agents. So today we will have a lecture about introduction to synthetic strategy of carbohydrate derivatives. But before our guest start the lecture, probably I would like also to introduce you to the audience here. So the audience who attend this lecture are a bachelor students from chemistry department of Pajajaran University, and also magister students from chemistry department of Pajajaran University, and the last is a bachelor student from chemistry department of Jambi University. So and also for all the students, the lecture today will be around 1.5 hours, and also we will follow with half hours of discussions. And regarding the discussions, the students can try to ask the question later on in the discussion sessions, or you can also try to type in the chat box in the Zoom meeting, or the student who attend through the YouTube, you can also try to type in the chat box. And at the end of the lecture, all the students will have an assignment to make a summary from this lecture, and then the student will collect this assignment to us here, and then we will try to give them some assignment score. So probably that's the rule for our guest lecture today. I hope all the students can try to understand all the lecture, and if it is possible, technically, you can try also to switch on the video or the camera. Otherwise, if you have a problem in the internet connection, it is fine to have an audio. Okay, and the last, probably I have also to tell you here, Sensei. So we have also here our lecturer who attend this guest lecture, especially from the teaching team of synthetic of organic molecules from the university. So one of them is probably Dr. Dadan Sumiarsa, I think. Pak Dadan?
Yes.
Okay. Yes, I think there is Pak Dadan also. So, and probably the other one will join later on during the lecture. Okay. I guess it is your time to deliver the lecture.
Okay. Good afternoon from Chiba, near to Tokyo, to everybody. Now you are now 1 o'clock, 1 p.m. I guess. Yes, maybe I guess some of you are a bit sleepy because you took lunch just
Yes.
before 30 minutes. So I'm afraid if you will be sleepy, but I will give some lecture about introduction to synthetic strategy of carbohydrate derivatives. To start that, before start that, thank you very much for Professor Jamaldin for your kind introduction of me. I would like to start the lecture.
Okay.
Yes, this is the outline of this lecture. At first, I will talk about the fundamental of carbohydrate chemistry. This is a very basic chemistry. Maybe you can find this section on your some books of organic chemistry. And the second part is the principle of oligosaccharide synthesis and how to construct, especially I will focus on how to synthesis of sugar units and how to conjugate them selectively. Yes, I will start the first section. This is a fundamental carbohydrate chemistry. This slide is just translated to English that I always use for our students. Yes. Yes, this is the structure of glucose. This is the most abundant monosaccharide in our in nature. The structure is like this. This is a linear structure, and this glucose has a aldehyde group in atom C1 position, and C2, C3, C4, C5. These carbons have one hydroxyl groups as like this. And this is a classification of sugars. The smallest sugar unit that cannot be decomposed as sugar is called a monosaccharide. Disaccharides from disaccharide to 10 sugars are called oligosaccharides, and more than 10 sugars are called polysaccharides. So this means this is the structure of a sucrose. This is a disaccharide. When you hydrolyze this glycosidic bond, you will obtain one glucose and one fructose. And glucose and fructose cannot be hydrolyzed anymore. So glucose and fructose are monosaccharides. And this is a cellulose that is composed of more than 3,000 glucoses with beta 1,4 linkages. And this cellulose is called the polysaccharides. Yes, and this is very important to introduce Fischer projection. Fischer projection is established by Dr. Emil Fischer, who received Nobel Prize for his great contribution to carbohydrate and protein chemistry. This is a Fischer projection, and this one is Fischer projection. This projection represents this structure. This means main chain is like this, but side chain is every time side chain is upper of this chain. This is a principle of a Fischer projection. And when you change the structure like this, this is a linear structure, but you can change this structure like this. This is the same structure. And when this alcohol attacks here, this glucose can be a ring structure. Yes, and in sugar, there is of course, sugar is a chiral compound, so sugar generally has enantiomers. And in Fischer projection, the enantiomer with hydroxyl group at the bottom chiral center. This means in the case of this structure, there is a 1, 2, 3, 4 chiral centers. And if the hydroxyl group at the bottom chiral center, this means that this carbon. And when the alcohol is left side, this is called L sugar, and other one is called D sugar. So this is the structure of L glucose, and this is the D glucose. In nature, most of the glucose is D form. Yes. Not only glucose, but many natural products such as are D sugars. This is the most simplest sugar, D glyceraldehyde, but there is almost no L type. And ribose is D, and the glucose is D, and the fructose is D. Most of them are generally D form. And the characteristic point of sugar is a cyclic structure. Generally, aldehydes and ketones form the hemiacetal when reacting with the alcohol under acidic conditions. This is the schematic image of this sentence. This is aldehyde RCHO, and when this aldehyde reacts with one alcohol under the proton catalyst and generates a hemiacetal structure. Generally, hemiacetal is not stable, so generally it decomposes to aldehyde or change to acetals. But sugar has a hemiacetal structure. For example, glucose exists as a pyranose ring in aqueous solution. This means this is a pyranose form. Because this structure is very similar to a pyran. So this six-membered ring is called the pyranose form. And pyranose ring in aqueous solution forms a hemiacetal with the C5 hydroxy group and the aldehydes. This means, for example, this is a hemiacetal form, and when this ring is opened, it changes to the linear structure like this. And when this alcohol, oxygen atom of alcohol attacks to the aldehyde group, it cycles again, but depending on the phase of this alcoholic attack, this can be beta and alpha, alpha form and beta form. And so there is these compounds are under equilibrium, and this I don't know, I don't have to say this ratio of alpha and beta forms depending on the configuration of the hydroxy group on C1. Okay, when monosaccharide adopts a cyclic structure, a chiral center, this is called the anomeric center, is formed at the carbon-carbon. Yes, this one. This carbon is called the anomeric position. This carbon is beside of the ring oxygen. This is called the anomeric position. And two diastereomers, alpha form and beta form, are produced depending on the direction of the cyclization. And in aqueous solution, these diastereomers are generally in equilibrium. The phenomenon in which the optical rotation changes when this equilibrium is reached is called mutual rotation. Yes, if you add a pure alpha form into water, after several hours, this equilibrium is reached to completely equilibrium, and optical rotation is changed from this value, but for several other values, for example, plus 50 or something like that. And I want to introduce a very specific chemical effect in carbohydrates. This is called the anomeric effect. As you know, when cyclohexane derivatives are under equilibrium with axial or equatorial form like this. For example, this is a cyclohexane with methoxy group like this. And there is a two conformers. One is an axial form and this is an equatorial form. And as you know, generally, the axial position has a very steric hindrance because of the 1,3 diaxial repulsion. So generally, in cyclohexane derivatives, generally this equatorial form is dominated. But on the other hand, functional group on the carbon atom, adjacent to the oxygen atom in the six-membered ring. This means, this is just cyclohexane form, but this is similar to cyclohexane form, but there is a ring oxygen atom near to the functional group. And if this kind of oxygen atom is positioned at a cyclohexane form, opposite to cyclohexane case, but most of compounds show this kind of axial form is stable. For example, this methoxy group is axial form, and this is a equatorial form. But in carbohydrate chemistry, this axial form is dominated to equatorial form. This effect is called the anomeric effect. Today's lecture, I will tell you many times of this effect. So please remind this effect. And there is another effect. This is called the reverse anomeric effect. I told you before, axial positioned functional group is dominated than equatorial group in sugar unit. But if this is there's a cationic anomeric groups is attached to anomeric position, generally equatorial positioned group is more stable. This effect called the reverse anomeric effect. So this is a completely opposite to anomeric effect. If the functional group is anionic or neutral, generally anomeric effect works well, but only in cationic group, reverse anomeric effect can be dominated. Yes. From here, I will introduce some examples of reaction of monosaccharides, and this slide shows this is a mistake. Esterification. This is aterification, but esterification. Yes, sugar hydroxyl group generally react like alcohols. This is almost the same, shows the same reactivity with some ethanol or butanol and so on. So reaction of acid chloride or anhydrides in the presence of a base produces esters. This is examples of the reaction. This is a beta D glucopyranose. This is a beta 4 of glucopyranose. And when you treat this compound with this is acetic anhydride in pyridine and at 0 degree and wait 24 hours, and you will obtain 5 acetylated compound. This is called a penta or acetyl beta D glucopyranose. And generally, you can obtain a very good yield. For example, this example shows a 91% yield. Generally, high yield is expected. And if you synthesize carbohydrate units, for example, monosaccharide or disaccharide and trisaccharide, most of the case, the first reaction is acetylation of sugar unit because sugar has many polyalcohols. So this means sugar is not soluble into most of organic solvent. So this is a first reaction for two purposes. One is to protect alcohol, and other purpose is to solubilize the sugar into organic solvents. Yes, and next I will talk about esterification. Yes, isomerization occurs around the atomic position in the Williamson ether synthesis synthetic method, because Williamson ether synthesis requires a strong basis. So generally, when this carbohydrate forms a link open form, there is an aldehyde. So if you use a strong base, the C2 position of hydrogen of C2 position will be removed by a stronger basis and react with other compounds and resulting in decomposition. So you need a very mild condition to make ethers. So this is one example. Reaction of iodide methane with silver oxide result in methyl esterification of hydroxyl group. Yes, when you treat this glucose unit with excess amount of methyl iodide with silver oxide, and to form this esterificated compound. This is called alpha D glucopyranose pentamethyl ether, and this reaction also the yield of this reaction is also a very good 85%, and generally you use this reaction to determine the glycosidic bond of polysaccharide. Yes, and next I will show you the producing glycosides. As I told you before, hemiacetals react with alcohol and the acidic condition to produce acetals like this. Sugar is hemiacetal like this. This is the anomeric carbon, and this is anomeric hydroxy group, and this is a ring oxygen. And when you react hemiacetal sugar unit with alcohol in the presence of catalytic acid, you will obtain acetal with water. Yes. So hemiacetal monosaccharides react with alcohol and acidic conditions to produce generally glycosides. So hemiacetal, this glycoside is acetal bonding. This method of glycoside formation is called the Fischer method, because Emil Fischer developed this method. And glycosides have the functional group name of the glycosidic bond followed by O's changed to O side. I will tell you about it. This is the starting material, beta-D glucopyranose, OS. This is the OSE. And when this compound generates a glycosidic bond, you should change the name to glucopyranose side, O side. This is O side means glycoside. And you put this functional group. This is the methyl group. So methyl alpha D glucopyranoside. And alpha form is axial form, and beta form is equatorial type. So this is a methyl beta D glucopyranoside. You see, this reaction affords this axial positioned methyl glycoside dominantly than a beta glycoside. You know, this is a 66% and this is a 33%. This is because of the anomeric effect. Glycosides are widely distributed in nature and many of them are biologically active. For example, this is a carditonic digitoxin. This is a trisaccharide with a steroid, and they are connected by a glycosidic bond. And this can be drugs for heart diseases. And this is a very ancient method to generate a glycosidic bond. Glycoside are generally obtained by mixing glycosyl bromide. This is a glycosyl bromide means glucose with bromine atom at anomeric position. This is called glycosyl bromine. And this glycosyl bromine, when this glycosyl bromine is treated with some alcohol with a silver oxide to generate a glycosidic bond like this. This is AROH is a allyl alcohol. This means aromatic alcohol. You can use any aromatic alcohols, your phenols, in the presence of this silver oxide to generate this kind of glycosidic bonds. This is developed by Professor Koenig and Professor Knoll. So this is called the Koenig-Knoll reaction. And this was developed 100 years ago, but this is still effective to generate glycosidic bonds, especially with allyl alcohols. The Koenig-Knoll reaction proceeds under SN1 because, you know, this glycosyl bromide has an alpha configuration at anomeric position, but you will obtain absolutely beta one. You can obtain only beta form. So this must be SN1 reaction. Yes. This is the reason. This is because the carbonyl oxygen of the C2 ester. This means this is a C2 position, and the C2 has a acetyl group. So the structure is like this. When bromide is removed by a silver cation, and this kind of intermediate is generated. And this carbonic oxygen atom attacks to the anomeric center and to produce this kind of intermediate. This is called orthoester form, and this orthoester form generates the OC bond from alpha phase. So alcohol attacks from only beta side and to generate this beta glycoside only. So this is called neighboring group participation, and I will explain again the next part. Yes, and this is the schematic image of how to produce a disaccharide in our body. Carbohydrates exist as complex carbohydrates that are linked to a protein and a lipid via glycosidic bonds. So generally, it calls glycoprotein and glycolipids. And complex carbohydrates are synthesized by sugar nucleotide and glycosyl transferases. Yes. At first, the glucose reacts with ATP, and anomeric position is phosphate, changes to a phosphate. This is called a D-glucosyl phosphate, and react with the uridine 5' triphosphate. This is called a UTP, and this compound is converted to this kind of compound. This is called the UDP glucose. And then the glycosyl transferase, this is an enzyme to generate the glycosidic bond, uses this UDP glucose as a glycosyl donor and react with some alcohols for example, this is a protein alcohol. This is a maybe side chain of a serine, and this alcohol is glucosylated and to generate a glycoprotein. This is a schematic mechanism of biosynthesis of a glycoside. Okay, and we have 8 essential monosaccharides as shown. I will show these sugars. The human needs 8 monosaccharides to maintain homeostasis, and generally the galactose and the glucose and the mannose, they are very simple aldohexoses, and L-fucose. This is a few examples. Fucose is a natural one. Natural fucose is L form. Is a C6 deoxygenated aldohexose. This one. Other monosaccharide have alcohols at the C6 position, but only fucose doesn't have alcohol at the 6th position. And other 4 monosaccharides are shown here. N-acetyl D-glucosamine and galactosamine and mannose are N-acetylated amino sugars. N-acetylated means here, N-acetyl group is attached to a C2 position instead of alcohol. So this is called the N-acetyl glycoside. This is N-acetyl glucosamine, N-acetyl glucosamine, the galactosamine, and this is a N-acetyl D neuraminic acid. This one here is also N-acetyl group. And D-xylose, this is a D-xylose is a very simple aldopentose. This is only pentose because there is no carbon atom at the C5. So this compound has only 5 carbons. And all essential monosaccharides are biosynthesized from glucose using some epimerase or some aldolase and so on. But ingestion is more energetically efficient. Yes, you can produce all monosaccharides from glucose, but to synthesize them, you need a big energy. So generally, we took these essential monosaccharides from food. And disaccharides, monosaccharides linked together by glycosidic bond. This is called disaccharide. A disaccharide in which the glucose alpha-4 linked is maltose. This is the structure of maltose. Both sugar units are glucose, and they are connected by a glycosidic linkage from 1 to 4 and alpha linkage. So this is called 1 to 4 alpha linkage. So maltose have a 1 to 4 alpha glycoside. And opposite to that, when 2 glucose unit is linked with a 1 to 4 beta linkage, this is called a cerobiose. So this is the structure of cerobiose. And just the different point is if both glucose unit is attached beta or alpha, alpha linked is maltose, and cerobiose is linked with a beta form. So the difference is only this one, but the biological properties are completely different because we can decompose this disaccharide by using a maltase. We have this enzyme in our in our mouth, and you can generate 2 glucose units, but we don't have any beta glucosides, so we can't degrade this one enzymatically. So we can't use this compound as an energy. Yes. Okay. Lactose is a disaccharide in which D-galactose is beta linked to C4 of D-glucose, just like this. This is a galactose unit, and this is a glucose unit. And these two monosaccharides are linked by beta 1 to 4 linkage. This is called as a lactose. This is the main content of milk. And the difference of cellulose, this is cellulose and this is lactose. The difference is only the configuration of this point. When this is a equatorial position, this disaccharide is cellulose, but this lactose have this axial alcohol. So this unit is monosaccharide is galactose, but we have a beta galactosides. So we can decompose this disaccharide and to generate one galactose unit and one glucose unit. And we can use them as energy or to construct other monosaccharides. Yes, this is maybe this is the last part of sugar chemistry part. And I will introduce cell surface glycans and glycovaccines. And glycans plays an important role in cellular recognition in vivo. And there are 4 blood types depending on the structure of sugar chains on the surface of red blood cells. And blood with a different sugar chain antigen will coagulate when mixed like this. For example, when your blood type is A, you can accept A-type and O-type blood, but no, A-type and AB-type blood, but you can't accept B-type and O-type blood because there is a big inflammatory reactions, and after that you will die. This is a figure of a donor blood type and acceptor blood type, and only circle conjugation is permitted because of the stronger inflammatory reaction. This is because of the structure of the A-type, B-type, O-type glycan. I will show you the structure. There is no big difference. This is the terminal structure of blood type A glycoproteins. We have a Elf course and linked with the alpha 1 2 linkage to D-galactose. And D-galactose have a 1 2 3 linked N-acetyl D-galactosamine. And this D-galactose is linked by using a 1 2 4 beta 1 2 4 form to N-acetyl D-glucosamine. And between protein and this monosaccharide, there is almost 6 oligosaccharides and connected to protein. And the difference of blood group B of comparing to A, the difference is only here. This is N-acetyl D-galactosamine, but in blood group B, the D-galactose is attached. So only the difference is, the functional group of C2 position of galactose. Blood type A have a N-acetyl group at the C2 position, but blood type B has only alcohol. The difference is only that. But our body's antibody recognizes these types of structure. And if you are blood type A and your antibody recognizes beta type red cell as an invader, and you will kill this red blood cells. And after that, you will die. This is a mechanism of the diffusion. And the structure of a blood type O's oligosaccharide, both galactose and galactosamine is absent. Just a trisaccharide is attached to a terminal point. So the difference is only the structure of this part. and O is lacking this carbohydrate. And this is the reason no, sorry, I forgot how to say. And this is a reason to make a big diffusion by antibodies. Sorry. Okay, and being inoculating the body with the sugar chains expressed in specific cells and bacteria or viruses, the antibody against the sugar chains is strengthened and the resistance to diseases is obtained. And chemical synthesis of sugar chain is actively carried out to produce sugar chain vaccines against cancer cells, pneumococci, and the AIDS virus, and the malaria, and so on. This is called the Lewis-Y hexasaccharide, and this is a terminal structure of some bacteria. And this hexasaccharide is synthesized around 30 years ago by an American chemical group, and they are producing vaccines by using this hexasaccharides. Yes, this is the last part of first part, and I want to continue to a second part. This is the main topic of a principle of oligosaccharide synthesis. Yes, before that, I want to tell you the importance of oligosaccharide on our cell surfaces. Generally, we have glycoprotein and glycolipids, and they have oligosaccharides. So this means when you can see the surface of a cell, maybe you can see you can recognize that our cell surfaces are completely covered by oligosaccharides, because oligosaccharides are very big have big structures. So, and there are many types of oligosaccharides that exist on our cell surfaces, and this serves not as energy or structure to keep a structure or a sweetener, but works as a signaling molecules with other molecules. For example, to bind with protein toxins or bacteria and viruses, and they enter to cells by attaching to the specific carbohydrates. And these oligosaccharides are related to cancer metastasis and fertilization and cell differentiation and so on. So recent 40 years, carbohydrates on cell surfaces has revealed as to serve as a recognition signals in our body. Yes, this is a very small number of example of bioactive oligosaccharides. And this is called KRN7000. This is a glycolipid isolated from C. I don't know how to say in English at all, but C, I don't know how to say, C animals. And this KRN is an abbreviation of Kirin. Kirin is a Japanese beer company, and they isolated this compound. And they found that this has a very strong immunopotentiating activity. This shows, especially this shows a strong anti-cancer activity. And the structure is very simple. This is alpha galactose, and this is attached to this it is called phytosphingosine. This is one kind of lipid, and this trisaccharide is called the GB3, and this trisaccharide is a ligand. This is a ligand is a structure needed to be bound to some proteins. So this trisaccharide structure is the sugar, oligosaccharide that recognized by virotoxin, and the virotoxin is produced by a pathogenic E. coli, and especially O157, and this virotoxin is very strong toxin against, especially against your colon and kidney, and some child or old people will die when they are infected by pathogenic E. coli. And this very complicated structure is called N-linked dodecasaccharide. And this works as a protein refolding signals in our body. And as shown like here, oligosaccharide in our body cell surfaces have a very complicated structure, but it's very important that oligosaccharides should have the exact structure for their bioactivity. Next, I will show the one example. This is a GB3 structure. The exact structure is from terminal structure. Galactose attached to galactose's 4 position by using one alpha 1,4 linkages. And this galactose is attached to a 4 position of glucose using beta 1,2,4 linkage. This is the exact structure of GB3, and this binds to virotoxin very strongly. But when you change the structure, for example, you epimerize this actual alcohol to equatorial form, and this is the glucose, or move to 3 position. If you move this galactose position from 4 to 3 position, or this you change from alpha form to beta form, or remove this galactose part, these compound never attach to virotoxin. So this means virotoxin recognizes this trisaccharide structure very, very seriously. So exact structure is required to express the bioactivity. Okay, this is not an important part for this structure. Yes, I will show the oligosaccharide difficulty of oligosaccharide synthesis. For example, synthesis of construct DNA chain is not so difficult because the linkage is ester, phosphate ester with alcohol, with generate alcohol react with some phosphates, and to connect just one bonding. And reaction site is only one, from this one. Only this one react with this site. So reaction site is only one. And there is no stereoisomer because just make esterification. And any chiral center join in the reaction. So there is no stereoisomers in this reaction. So generally, DNA or RNA synthesis is not so difficult in nowadays. And similarly, the peptide synthesis is not so difficult because the linkage is amide bond. So there is no difficulty to generate this bond. And reaction site is only one because the reaction is performed by one amine group and one carboxyl group. So if you protect other site, you can just react with this one, and there is no stereoisomer. So this is the reason peptide synthesis is not difficult like a DNA chain. But synthesis oligosaccharides, there is a two big problem. One linkage is, this linkage is a glycosidic bond. As shown you, there is a two types of binding, and alpha linkage and beta linkage. There is a two stereoisomers, and generally monosaccharides have at least 4 or 5 alcohols. So this means reaction site is 5. So totally 10 isomer will be generated. So this is a very difficult point of oligosaccharide synthesis. Yes, so regulation of stereochemistry and position of glycosidic bond is of great importance in carbohydrate synthesis. Yes, this is a principle of general oligosaccharide synthesis. Yes, at first, you must prepare the 2 units. This is called glycosyl donor and glycosyl acceptor. And glycosyl donor is a unit to give a sugar unit to other alcohol. And glycosyl acceptor is to accept sugar part from glycosyl donor. Yes, we have to prepare both unit before making glycosidic bond. Generally, to prepare glycosyl donor, at first introduction, you have to make an introduction of a leaving group at anomeric position like this. Generally, the X is some thioether or some halogen, like a Kenny-Knoll reaction and so on. And other alcohols must be protected not to condensate by itself. So donor should, all alcohol should be protected. And next, to synthesize glycosyl acceptor, for example, if you want to make a glycation at this point, you must protect anomeric position and 2, 3, and 6 alcohol by protective group. And you must liberate only this alcohol, this site. Yes, and there is another point. Each sugar hydroxy group, I put only P. This is an abbreviation of a protective group, but you must introduce protective, appropriate protective group. Because if you want to liberate only here, you must protect at first, introduce some protective group at the 4 position and protect other alcohols by another protective group. That is stable, that is unstable, that is stable in the condition to remove the protective group at this position. After that, you will obtain only this compound. Yes, this is one example to make a glycosylation. And this is a glycosyl donor with glycosyl donor has a leaving group at here. And when you use some compound, this is called a promoter. And the promoter can remove this leaving group. Generally, the promoter is a strong acid or some halogen derivatives and so on. And when you put the promoter to a donor, and X is relieved from a glycosyl donor and generate a carbocation intermediate. And alcohols attacks alpha phase or beta phase, and it depends on the condition. And you will obtain the alpha and beta. And if you need a beta type, and you must isolate beta type or synthesize stereoselectively this beta one. And finally, they protect all protective group, and you will obtain, for example, lactose like this. This is a very basic principle of oligosaccharide synthesis. Yes, but there is a big problem, and how to differentiate sugar hydroxy group. Because, for example, this is the structure of D-galactose, and D-galactose have 5 alcohols, and especially for undergraduate students, maybe you think most of the alcohol have a similar reactivity, I guess. Yes, when I was a undergraduate student, I thought like this, but they are completely different. Yes, like this. This alcohol is a primary alcohols. Yes, maybe you understand this, but other one is a secondary alcohol. But there is a big difference. Especially anomeric positions alcohol is a hemiacetal hydroxy group. So this alcohol can be removed easily by acidic condition and to generate a glycosidic bond. And the other three alcohols, there is a two difference. And these alcohols are oriented at the equatorial position. And this one is oriented at the axial position, So, generally, because of 1,3 diaxial repulsion, this axial position alcohol is less reactive than other one. Yes, because when the reagent reach to axial position, there's a big steric repulsion. So generally, these alcohols are more reactive than this. So, and there is another properties. The relationship of this and this alcohols are 1,2 trans diol. This means the diol at first position and second position is transformed. This position alcohol is located at below of hydrogen, but this position alcohol oriented upper position. So this is called 1,2 trans diol. And comparing to that, the relationship of this alcohol is completely different because both of alcohols are located upper side. So this diol is called 1,2 cis diol. And I forget to put the word, but the relationship of this and this is called 1,2,1,3 diol because one alcohol is attached to first carbon and second alcohol is located 1, 2, 3 in third position. This is called 1,3 diol. So firstly, there may be no difference between all alcohols, but each alcohol have a very characteristic reactivity. So generally, using this difference, you can introduce some protective group selectively. Okay, next I want to introduce some protective group used for carbohydrate synthesis. At first, I will introduce ester. Ester is introduced by a condensation with some carboxylate or using anhydrides and acyl chloride. And how to remove is generally hydrolysis. But this condition is required a strong basic or acidic condition. So generally, we use ester exchange reaction by using alkoxide and in alcohol. This is a very popular way to remove ester in carbohydrate chemistry. This is some example of ester. Most used ester group is acetyl group because it's very easy to introduce. The structure is like this. Then the abbreviation is AC. So please remind it. Don't forget it because after 10 or 50 minutes, I will use this word so many times. And the acetyl group is the smallest ester, not smallest, the second smallest ester. And this is a benzoyl ester. This is just this acetyl methyl group is changed to a phenyl group. This is a benzoyl group, and the abbreviation is a BZ. And this one is also popular as a protective group. And the size is the middle size comparing to acetyl group. So this property makes a slightly radioselective. Because when you put one equivalent of benzoyl chloride, you can protect selectively primary group. And this is a pivaroyl group. You know, this ester has a very big tertiary butyl group. So the size is very big, and this reaction completely shows radioselectivity. But the problem is, generally we use pivaroyl chloride, this structure with chloride, but just 5 or 10 years ago, this is decided a toxic compound in Japan. So we cannot use these compounds. So it's very sad, I love this protective group, but I can't use this compound. So it's sad. So I understand your situation, Professor Jamaldin. It's a very stressful condition. Yes, and next is ether protective group. This is also often used in carbohydrate synthesis. Ether groups can be introduced by a nucleophilic substitution with some alkyl or allyl chloride or allyl bromide. And this condition requires a strongly basic and William ether synthesis conditions. So, and at first I told you this condition is not suitable to introduce the ether group for low sugar unit. This means natural style. But when you protect anomeric position, you can use this condition. And how to remove this group is hydrolysis. And generally in the book in organic chemistry, generally ether can be removed by a strongly acidic condition. But if you use this condition, sugar part and glycosidic bond is completely decomposed. So you can't use this. So we use a very special ether group as shown here. And one is methyl ether, and but it should be only anomic position. If you put anomic position at this methyl ether, you can remove just acetylysis. This is not strong acidic condition, so you can remove selectively. But if you introduce this methyl group into other alcoholic group, alcoholic position, this is just ether. This if you introduce methyl group at anomic position, this is acetal, so it's easy to remove. But if you make an ether group by using methyl group, there is no way to remove selectively. So we use this methyl ether only at anomic position. And other one is some special ether group which can be removed very, very simple way. One is allyl group. The structure is like this. Generally, there is a double bond between this carbon and this carbon. So this structure is called the allyl group. And when you put oxygen out here, this is called the allyl ether. Because allyl ether can be selectively cleaved by isomerization to vinylic ether. And vinyl ether is a very, very unstable and weak basic condition. And you can remove this allyl group very, very selectively. we often use this compound. But most abundant ether group is a benzyl group. You know, this one, phenyl group with methylene group with O. This is called the benzyl group. Abbreviation is BN. This is also often appeared in the later. And how to remove is this is hydrogenolysis by using using a hydrogen gas with very small catalytic amount of palladium, and you can remove this benzyl group as a toluene. You know, if there is a O atom, hydrogen attached to this carbon and this oxygen, and the oxygen changes to alcohol, and this benzyl group is changed to toluene, and you can just walk up. You can filter to remove a palladium, and after that, when you concentrate the filtrate, you can obtain the pure compound. And especially for undergraduate students, you are happy to perform this reaction because you don't have to make any chromatography, because silica gel chromatography is one of the tough experimental procedure. Sometimes you must be patient for several hours, or sometimes 12 hours and so on. But in this reaction, you don't have to do that. This is a very easy, and you can save the times at this day. And this is called the 4-methoxy-benzyl group. This is a benzyl group with methoxy group at para position. So this is the abbreviation PMB. This means para-methoxy-benzyl. And what is the difference between a benzyl and a para-methoxy-benzyl is this can be also removed by hydrogenolysis, but this group can be removed by a single electron oxidation. So this means if PMB group can be selectively removed in the presence of a benzyl group. So this is a very nice property of a PMB group. And this naphthyl group is also have this kind of a property, but the difference is that PMB is generally unstable under the acidic condition, but NAP group is very stable against under acidic condition. So we want to use a NAP group instead of a PMB group, but the problem is the price of the reagent to introduce a NAP group is very expensive, extremely expensive. Generally, we use a PMB chloride to introduce a PMB group. The price is around, in your country, for example, 100,000 rupiah for 10 grams of a reagent. So it's not so expensive. But for NAP chloride, costs around 3 million rupees for 5 grams, so very expensive. So I'm not rich, so I always use this PMB group. But if PMB doesn't work at all, I will use a NAP group with very small amount, and I will try the glycation reaction. Yes, and this silyl ether is also used to protect sugar hydroxyl group, and this can be introduced by a nucleophilic substitution with RCl, no, not RCl, SiCl or SiO sulfate. And generally, the condition is a mild basic or mild acidic condition. And it's the very specific property of silyl ether is this can be removed by a fluoroanion. So this is completely mild condition, and this fluoroanion generally doesn't affect the ester and ethers. So this means silyl ether is always can be removed selectively. So this is some example of a silyl ether, and the major one is a tertiary butyl dimethyl silyl group. This is a one tertiary butyl group, and the two methyl groups are attached at the silicon atom, and the abbreviation is just TBDMS. This is TBDMS, and you know, as you can suspect, and this has a very big size. So the reaction is highly radioselective. Generally, at first, primary alcohol reacts this one, and if you put the 2 equimolar of a reagent, you will obtain a equatorial oriented secondary alcohol will react this reagent. And there is another derivative, the diphenyl version and the triisopropyl version, and they also have a big size, so the reaction is generally highly radioselective. But there is a bit difference, you know. TBDPS group is very stable under acidic condition, like a glycation, but TBDMS group is not stable at all. And the TIPS group is very weak under acidic condition, but TIPS group is very, very stable under the strongly basic conditions. So you have to choose carefully with considering the synthetic strategy for your target compound. Yes, this is also very specific protective group. This is a cyclic acetal like this, because the sugar is generally have polyols. So you can make cyclic acetals using 2 alcohols of sugar. So generally, this group is introduced by acetal formation using a carbonyl compound or its dimethyl acetal form under acidic condition. This means, you know, when you use, you know, dimethyl acetal form, and generally acetal formation is equilibrium, under equilibrium. And when you put water, the cyclic acetal converted to diols. But when you remove water, you can obtain a cyclic acetals in very good yield. But if you use this dimethyl acetal, you know, methanol have a low boiling point. So when you put some round bottom flask, if you attach this reaction mixture to a evaporator, when reaction proceeded, methanol will be generated, and generated methanol is removed via evaporator. So this means you can obtain a cyclic acetal soon. So this is a very nice system. And this cyclic acetal can be removed by very weak acidic hydrolysis or just hydrogenation like a benzyl group. So we use this cyclic acetal so much. And the normal one is benzylidene acetal, means pH, and R dash is R prime is H, and R is a phenyl, and this is a benzylidene acetal, and this shows a highly radioselectivity to 1,3-diol, and paramethoxy version is also effective to protect 1,3-diols, and there's other one, isopropylene ketal. This means R and R prime is a methyl group, you know, and this is this is derivatives from acetone, and this is isopropylene ketal is very radioselective to 1,2-cis-diol. This is a very important point. This can be formed only to 1,2-cis-diol, no trans-diol. So if you differentiate 1,2-trans and 1,2,6 diodes. Generally, we use isopropyl ketones to protect 1,2,6 diode. Yes, this is a protected group for anomeric hydroxyl group. Yes, methyl group is already introduced, and allyl and benzyl and paramethoxyphenyl, and they are also used to protect anomeric position. And there is other protective group, thioglycosyl group. For the example is like this: phenyl and methyl and ethyl ether. Yes, the abbreviation is S-phenyl, S-methyl, methyl, and S-ethyl. And this can be a very nice protective group because this can be removed by a hydrolysis with a halogen cation, almost neutral condition, and you can remove them selectively. And next nice point is this thioglycoside can be used as a glycosyl donor. So this can be protective group, but a leaving group, selective leaving group of a glycoside. Yes, this is an example of a synthesis of a glycosyl acceptor. If you want to make a glycosylation at 4 position or 6 position of galactose, you can synthesize like this. This is a D-galactose. At first, you protect anomeric position by using methanol with a catalytic amount of sulfuric acid. And this is a Fischer glycosylation condition. So you can obtain the anomeric methylated galactose derivatives. This is a galactose protect with anomeric position protected galactose. Yes, next, you must differentiate 4 alcohols. Yes, generally, at first, we perform benzylidination. This is a cyclic acetal. This reagent is a very selective to 1,3 diode. So this means this is a, please remind, this one is 1,2 trans diode, and this one is 1,2 cis diode, and this is 1,3 diodes. So generally, benzylidene group forms at this and this oxygens, and to generate cyclic acetals. And after that, 2 hydroxy group is protected by a benzyl group by using a benzyl bromide and sodium hydride. This is a very strong condition like Williamson esterification, but you have already protected anomeric position, so there is no problem to use a very strong condition, and you obtain the fully protected this compound. But when the very nice merit to use a benzylidene acetal is you can selectively cleave the one of these bonding. For example, when you use lithium aluminum hydride with trichloroaluminum in ethanol, you can obtain this compound. This is not just cleavage, but regioselective cleavage of benzylidene acetal. This means this reaction cleaves this CO bond and liberate 6-position alcohol. But this is acetal. At first, this carbon has 2 oxygen, but after that, this changes to a benzyl group. The reason is that this halide anion from La reduce this benzylidene group and to cleave this and generates alcohol, and this carbon has 2 hydrogen. This means this benzylidene group changes to a benzyl ether. This is called radioselective cleavage. And if you use this system, you can obtain a 4OH, this kind of a product. So if you can obtain two types of glycosyl acceptors by using different systems, and you can generate your desired compound by using a different system. Yes, this is an example of a synthesis of glycosyl donor. Yes, this is also start from D-galactose, and at first we generally acetylate this compound, and all of alcohol should be acetylated under the condition with acetic anhydride in pyridine, and you will obtain pentacetate like this. And then next, we generally the anomeric functional group is changed to a bromide like this. The mechanism is a completely SN1 reaction. At first, this acetoxy group is removed by a strong acidic condition and generate a carbocation, and then bromine anion attacks to anomic position to produce this glycosyl bromide. Because this reaction is anomeric position selective, because only anomeric position needs acetal. So this acetalic position is very weak against the acid, and it's easy to be accept nucleophilic substitution to generate glycosyl bromide. And the reason to generate the only alpha bromide is anomeric effect, and you will obtain only alpha bromide exclusively. And next, this is a thioglycylation using a thiophenol with a very weak base in DMF. This nucleophilic substitution must be under SN2 condition, and you will obtain the only beta form. And this is a phenylthioglycoside, and this can be a glycosyl donor and react with a glycosyl acceptor. You will obtain a disaccharide and so on. Yes, and I will skip it. Yes, this is the same. Okay, and this is the last part, and how to generate glycosylic bond stereoselectively. And this is a general procedure of a chemical glycosylation. And this is a glycosyl donor, and when you add a promoter to this system, and the leaving group is cleaved and generate this oxocarbenium ion. This is generated after cleaving a leaving group, and the lone pair of ring oxygen makes a double bond at the anomeric position, and you will obtain this oxocarbenium anion. And this is the equilibrium of carbocation, and then glycosyl acceptor attacks to anomeric position from alpha or beta, and you will obtain an alpha and beta glycoside. And generally, the alpha glycoside is axial position, and the beta is equatorial one. But there are some exceptions. So in carbohydrate chemistry, we call them another name. And this glycoside have the same direction. This oxygen and oxygen are located at below over this ring. So this is called 1,2-cis glycoside. Of course, this 1,2 glycoside, alpha glucoside, alpha galactoside, the included 1,2-cis glycoside. And other one is a transform. So this is called 1,2 trans glycoside. There is two types of glycosylic bonds. And as I introduced before, 1,2 trans glycosides can be selectively constructed by a neighboring participation at C2 acid group. And as I talked about it in first part, and whereas only few reports on standard method for 1,2,6 selective glycylation. So this means 1,2,6 selective glycylation still involves difficulty. This year is 2023, and first glycylation is developed at in 1910. So it has taken almost 110 years. But still, 1,2 selective glycylation is very difficult. So I talked about it, so I skipped this one. And how to control stereochemistry in glycylation. I will introduce some examples. One is solvent effect. For example, when oxocarbonyl anion is generated after activation by a promoter to a glycosyl donor, and when the solvent is ether, for example, diethyl ether, the lone pair of oxygen atom attacks to an anomic center to generate this kind of intermediate. And because maybe there is an equilibrium, alpha form and beta form, but this is a cation, oxonium ion. So stabilized by a reverse anomeric effect because it's a cation. So beta form is dominant. And then glycosyl acceptor attacks at the anomeric center from alpha phase and to generate alpha glycoside. Yes. And if you use acetonitrile, there will be a different effect. Lone pair of nitrogen atom attacks to anomeric center. At that time, this orientation have some polarity, and this effect, this structure accept stabilization by anomeric effect. So to this intermediate, the alcohol attacks to anomic center, and this is like SN2 substitution, and you will obtain a beta glycoside. This is a solvent effect system, but the problem is it's not completely effective one. It depends on the solvent system, and if you use both of the system, you can't obtain alpha or beta glycoside exclusively. You will obtain a mixture generally, but you will have a alpha or beta glycoside as major product by using this system. And this one is called in situ anomalization effect. When oxocarbonyl anion is generated before attacking by alcohol, because in the reaction mixture, there is many anions, for example, halogens or trifluoromethane sulfonate can be nucleophile, and this attacks to anomic center, and there will be a alpha form and a beta form, and generally X has a withdrawal group or very strong electron negative atom. So alpha intermediate is stabilized by anomic effect. So this alpha intermediate is stable, but this means this is not reactive. Yes, so beta intermediate is unstable, but this is reactive. So alcohol attacks from alpha side to like SN2-like substitution to generate an alpha glycoside. And this is an in situ anomalization method to obtain a 1,2,6 glycoside. And this is almost last slide. I would like to introduce a recent achievement by a carbohydrate chemist, how to introduce 1,2,6 glycoside. This is a neighboring participation by thioether at O2 of a glycosyl donor. And this is a great professor, Jan Boons, and he developed this system, and he introduced this ether group at 2 position. And when this oxocarbenium intermediate generated, this thioethers lone pair attacks to the anomeric position to generate this intermediate. You know, there is of course there is one possibility. This is a beta form, and of course alpha form would be produced, but alpha form is unstable because of the reverse anomeric effect. So this beta six-membered ring is dominated, and alcohol attacks only from alpha form to obtain alpha glycoside. This is one method, but this is not so abundant. It's not popular because this can be applied a very special case. And recently, this method is focused on by carbohydrate chemists. This is a hydrogen bonding mediated 1,2,6 selective glycosylation. And Professor Demochenko designed this kind of glycosyl donor. This glycosyl donor have a pyridine group at a 4 position. And this nitrogen atom can make a hydrogen bonding with a glycosyl acceptor. And this means alcohol of glycosyl acceptor is located at the alpha phase and makes alpha glycoside, 1,2,6 glycoside. Yes. And this is a last example. This is called the intramolecular agricon delivery system, IAD. This is a very special method to produce a 1,2,6 glycoside. And at first, you prepare glycosyl donor and glycosyl acceptor, but you should put the NAP group at a 2 position of a glycosyl donor. This NAP group works very important roles in this glycosylation method. At first, oxidize the alpha position of a naphthyl group, and this is a radical reaction, and this radical react with this alcohol to generate this conjugate. This is from a glycosyl donor, and this is generated from a glycosyl acceptor. And donor and acceptor is conjugated as one molecule. And from this situation, when you add a promoter to remove this leaving group, you know, when asymmetry is removed and this acceptors oxygen atom attacks to the center intramolecularly. So this is a very, very quick reaction. And this is completely SN2 substitution. And you will obtain only 1,2,6 glycoside exclusively. This is a very, very strong method to obtain 1,2,6 glycoside, but still have a problem. This cannot be applied for a wide range glycosylation. So the recent stereoselective glycosylation is still development, requires a development by new methodology without thinking about the already reported manner. So we have to continue to think and develop new methodology to obtain a 1,2,6 glycoside exclusively to develop carbohydrate vaccine or any other medical applications. Maybe this is the last slide. No. Yes, this is the last slide because just now it has passed almost 1.5 hours. So I want to finish the lecture. Thank you for your attention.
Okay, thank you very much, Sensei, for the very nice lecture. And I think all students can have many specific knowledge, especially.
I'm sorry, maybe Professor Jamaluddin, maybe you turned off the mic, maybe. No?
Is it? Can you hear me now?
I can't hear your.
Oke. Kalau yang lain udah bisa dengar saya nggak? Halo? Can anybody hear me?
Yes, we can, sir.
Okay. Sensei, can you hear me? Hello.
Sorry, I can't hear anything from you.
Okay. Just moment. And how about from other student? Can somebody speak up and try to speak again? Any student?
Okay.
Is it?
Okay.
Can you hear me?
Yes. Sorry. I
Okay.
had a problem. Sorry. I had a problem.
Okay. Yes.
Okay.
Yes. Again, I would like to thanks for the nice lecture. Probably before I give a time to the student to have a question to you directly or probably from the chat box,
Yes.
I would like to highlight something really important for the student here, especially how we can deal with the polyhydroxy compound here, which have different reactivity and also different conformations, but finally, with appropriate strategy, we can control the regioselectivity as well as the selectivity in reactions. So this is really important. Probably this is the key, what the student should try to summarize in their assignment letter after this lecture. Okay, probably now is the question sessions, and now I would like to give an opportunity to the student who raise the hand. Okay, so here is Finanta. Can you open the mic?
Halo, Assalamualaikum.
Okay. Waalaikumsalam. Okay. Would you like to directly deliver the questions with English or bahasa?
Bahasa Indonesia.
Okay. Just say okay, and then I will translate.
Izin sebelumnya perkenalkan, nama saya Finanta Yulianti dengan NIM F1C1211014. Saya dari Universitas Jambi. Di sini saya izin bertanya. Tadi dijelaskan bahwa suatu blokasa itu kan harus dilindungi dengan gugus pelindung gitu ya Pak. Di mana gugus pelindungnya itu tadi ada ester, ada ether, dan ada asetal silik kalau nggak salah. Nah, pertanyaan saya, dari gugus pelindung itu, mana yang paling baik digunakan dan sering digunakan, dan apakah ada spesifikasi khusus jikalau gugus pelindung ini khusus untuk glukosa ini? Jadi kalau misal gugus pelindungnya itu ester, nah ini khususnya untuk gugus pelindung glukosa yang jenis ini gitu Pak. Dan seterusnya.
Okay.
Itu saja, terima kasih Pak.
Okay, good questions. Okay, I'll try to translate for you, Sensei.
Yes.
So this is a bachelor student from Jambi University.
Yes.
So he would like to ask about the protecting group of these glucose compounds. In the few slides, you show typical of ester, ether, and also silyl. And all of those protecting group are commonly used in these reactions. But what she would like to ask is which one is the commonly used or the best, which can selectively probably protect some typical of glucose or other oligosaccharide.
Okay, it depends on what kind of glycosyl donor and glycosyl acceptor which kind of a product do you want? It depends on, and as I show you the example of the how to produce these glycosyl acceptors, and this is only one example how to synthesize of this compound. But in this case, generally the best protective group, but it's not general. But in some cases, the best is to protect ether group because ether is generally very stable. Again, comparing to ester. Do you understand? Yes, and but it depends on. Because if you if you want to use stereoselective 1,2 trans glycoside, if you want to produce this one, you must introduce a acyl group. This means ester at C2 position. So it depends on the what do you want to produce. But generally, if ester and ether both go well, generally we use ether because of the stability. Yes, and if we want to liberate one position in the presence of ether and acyl group ester, generally we use this silyl ether because silyl ether can be removed, selectively can be removed in the presence of ester and ether and any cyclic acetals. Yeah, so it depends on what do you want to prepare. Sorry, this is maybe this will not be nice answer for you, but if you have any other questions, don't hesitate to ask me.
Okay. Yes. So in principle, probably I can try to ask more what the student want to know. Can we just, let's say, utilize kind of steric hindrance to access any particular hydroxyl moiety in this kind of polyhydroxy compound? Or let's say a higher steric hindrance or lower steric hindrance, or any other parameter which can generalize this kind of selectivity?
Yes, and generally, and I showed the size of a protective group. This generally, this kind of cyclic group has a very big steric hindrance. So this reagent can generally approach it to primary alcohol. So when you put this kind of a reagent to D-galactose, that only this primary alcohol can be silylated. So, and if you want to protect firstly this 6-position alcohol, we use a silyl group. So like this, you must select the protective group very seriously. Or if we want to protect this 1,2-cis-diol, we can use isopropylene acetals because this reaction is very selective 1,2-cis-diol, like this. So we don't select the protective group not only by steric hindrance, but also the formation. Which one you want to form, protect. Yes, but of course, sometimes many protect or deprotection reactions are required because it's like a puzzle because generally it's very difficult to liberate only this secondary alcohol because because they are similar property.
Yes. Okay.
So if you want to obtain this one, firstly protect this one by its isopropylene group, and you protect this primary alcohol by silyl group, and then after that you will got the 2OH version like this.
Okay, I think it is clear enough, and probably move to the next question, which is related to this slide, I think. So there is a student from Pajajaran University, Rafa Raditya, want to ask if we have two kind of this secondary equatorial hydroxy. So which one is more reactive, and which factor we can try to distinguish between those two reactivity in during the reaction?
Okay, maybe you mean in this case.
In
this case, how to differentiate reactivity. Yes,
Yeah.
generally it's very difficult, but very great professor developed one methodology. Yes, when you use stannylene oxide, you know, stannylene, alkyl,
Okay.
dialkyl stannylene oxide.
Okay.
And yes, the stannylene oxide produces, stannylene acetal between here and here. This is not, yes,
okay.
this is not, covalent bonding, but there is some orientation or some chylation or like this. And this 1,2-diol generates the stannylene acetal, and the reactivity of this alcohol is increased by this formation. And then if you add just some alkyl bromide, you can alkylate only this alcohol. Yes, this is the case. Yes, the most difficult is to differentiate the 2 or 3 position alcohol in glucose. It's very difficult. Yeah, because there is almost no difference. So this
yes,
is
yes, yes.
very difficult. Yes,
Yeah.
to liberate 2 or 3, only 3 position. Yeah.
Okay. Okay, I think it is clear, right, Rafa? Can you understand?
Iya, Pak, udah.
Okay. Probably next one is from Angelia Heberina. So she would like about kind of strategic of the synthesis for this kind of structure modification in order to improve the bioavailability of the compound. So
okay.
probably this is general question, bioavailability of this kind of compounds.
Okay. Okay. One easy application is I don't know how to say, to detect some diseases of
yes.
our body. Yes,
Yes.
because some cancer, or especially lung cancer or some kind of a cancer, have a special carbohydrates. And if you synthesize this compound in big scale, you can use this sugars, carbohydrates, as a detector of these some kind of cancers. Yes, this is this has already applied as a marker, cancer marker.
Yeah.
Yeah. This is a very representative. Yeah.
Yes. Probably next one is about the mutarotations properties of this kind of compounds during the synthesis. How far this affected the synthesis strategy of this kind of mutarotations, influencing the diastereomic or stereo isomer formations.
Like this?
Yeah, yeah. Yes. Yeah.
Yes. So this phenomenon is completely depending on the anomeric effect or reverse anomeric effect. And and at the first part, I showed you about it from alpha form and beta form. The equilibrium between alpha and beta form of glucose. Yes, that is depending on anomeric effect. When you put if you put pure beta glucose, you will obtain 33% of alpha form. Maybe this is because of the anomeric effect. If there is no anomeric effect, you will obtain beta one only, or most of the product should be beta. But you will obtain alpha. This means it depends on the alpha, anomeric effect. So with other case, anomeric effect is very strong in the equilibrium. And this is also the equilibrium and alpha and beta form. But of course, alpha form is completely stable by anomeric effect, because generally this X has a very strong property of, for example, electron negativity and electron withdrawal activity. So this compound, this alpha form accepts a strong stabilization. Yes. So, but this stability decreases the reactivity. So in this case, beta intermediate only react with secondary or some tertiary alcohol to produce alpha glycoside. So this kind of equilibrium is completely, I don't know how to say, depending on the anomeric effect or reverse anomeric effect.
Okay.
It's
So
okay.
probably can we control this kind of equilibrium with some effect, kind of temperature or
Yes, exactly.
concentration?
Exactly. Yes, yes.
Okay.
As professor, you are really suggesting a very nice condition. Yes, this anomeric effect is not so strong. Yes, strong, but it's not an absolute method. So this reaction should be very under low temperature. For example, generally we use react. We make a glycosylation under minus 78 degree.
Ah, okay.
Yes, to stabilize this one.
Okay.
Yeah.
Yeah.
And to decrease the reactivity of this alcohol. If
Okay.
this reaction, if this alcohol attacks to alpha 1, in a higher temperature, it could be. So to remove this possibility, we always perform this reaction under very low temperature. Yes.
Okay. Good. Okay. Jobin, I think it is clear, right? Can you understand the explanations? Okay. Yes.
Yes, Pak. Iya, Pak.
Okay. Okay, good. Okay, dear students, is there any other questions you would like to ask? If no, I think the time is, yes, it is almost 2 hours in 8 minutes. So before we close the guest lecture today, so I would like to remind you all students, so you have assignment to proceed after this lecture is to make a summary about how we can control the reogeoselectivity and stereoselectivity in this kind of carbohydrate reactions. So once you finish the assignment, please write with your hand, not with your computer, okay, students? And then you can try later on collect all the assignments to the lecturer through the learning system or directly. Okay, I guess this is the time for us to finish the lecture, but before we close, I would like to have documentation. Probably we can take a picture all together. Please, all the students open the camera. And probably, Sensei, you could also try to end the sharing.
Okay, I will try it.
Okay.
Maybe like this.
Okay, yes. Please, all the students, could you please open the camera? Okay, there are 4 pages here who enroll this guest lecture. So I will take a picture 4 times. 1, 2, 3. Okay. And the second, 1, 2, 3. And then third one, 1, 2, 3. And then just hold on once more. I would like to pin Sensei as the main picture, and then we will take another picture. 1, 2, 3. Okay, thank you very much to all of you students and also Sensei. Thank you very much. And Prof. Kurnia send you a regard. He just landing from the plane for having a conference in outside Bandung. So,
yeah. I'm happy to hear that.
Okay.
Yeah.
Okay, once again, thank you very much. See you again next time. Wassalamualaikum warahmatullahi wabarakatuh. Okay. See you. Bye.